Hey guys, welcome back to another episode. Today, we're going to be continuing our socially awkward dancing algorithm, which is kind of a bit of... I don't know how to put it, so I'm just going to go ahead and describe it, and we will go from there. So, let's go ahead and open up Zernal, and get started. Zernal, there we go. Okay, so first things first, if you weren't here last Friday, you may have missed a good bit of stuff, and actually, I don't remember when I did this. It might not have been last Friday. I don't remember. I think it was last Friday. Again, I meant to stream this weekend. It's just on Friday night, I was up until like midnight, and I don't know, I can't get up at 5 o'clock in the morning when I go to bed at midnight. And same thing happened on Saturday night into Sunday night. So it was only really last night that I really had enough sleep to get up. And it's been kind of a recurring thing. It's just, I keep trying to get up in the morning and I can't. Like, it just, no matter what I do, I just can't get up anymore. Which is a bit of a pain and a little unfortunate because it means that I miss a couple episodes here and there. I wanted to keep a super consistent streaming schedule, but, you know, the way I see it, Twitch is good, it's useful, but I feel like, I don't know, I feel like I'm the only one doing this kind of stuff on Twitch. And it kind of makes me feel like I'm doing something a little bit wrong with it. You know, like maybe I should, maybe the material is just not meant for Twitch or something like that. I don't know. We'll see. Anyway, so what are we doing? Well, there's this thing called a Kuromoto Oscillator. The idea is relatively simple. We have some sort of theta that varies as a function of time. So the dot is theta over dt. Is going to be equal to some sort of natural frequency of the object we're talking about, where we'll be talking about the object I. And then we say this is plus some sort of sum for, let's say, j equals, I don't know, 1 to n, for some sort of function that's related to the difference between the I minus j. But I think they actually do j minus I. It doesn't really matter that much as long as you have the difference in here. Okay, so this is kind of what we're talking about here. We have some sort of phase and some sort of frequency and some sort of function that's dependent. Now, typically, this is a sine or something like that. And so we have some sort of sine of theta j minus theta I. Okay, now what exactly does that have to do with dancing? Well, here's what we've got. Page, new page before. This guy right here, this is Steve. Steve is socially awkward. He doesn't know how to dance. He's always pent up in his lab. He never has any time to talk to people. However, he wants to talk to people. He wants to socially interact. So he goes to a party. When he goes to the party, he sees the following. Everyone, all the other people, they're all dancing. So here we'll have a whole bunch of people here. And they're all just oscillating via some sort of sine wave. One thing to note is they all have the same phase, because they're all dancing together, right? And so here they are, they're all dancing, and Steve then pops right into the middle of the dance floor. He says, okay, I'm just gonna pop in right here. I'm just gonna start dancing. However, he initially dances at the wrong frequency, and everyone is kind of repelled away from him because he's a horrible dancer. So these guys go this way, these guys go this way. But as he starts to dance to the right frequency, he becomes socially accepted, and everyone is then attracted to him. So they go this way and this way. With the force of attraction, or the force of repulsion, force, is going to be equal to some sort of function. So we'll say a force of attraction of him, so how attractive he is. A force of attraction from everyone else, how much they want to be accepted. And then times some random variable r, where r is going to be how far away you are from Steve. So in some sense, this makes a good amount of sense. The idea is that as the dancers are further away from Steve, they're going to feel a stronger force towards him, and as they're closer, they're going to feel a weaker force. Now we're going to be solving this with the Verlet algorithm, similar to what we did with the what did we just do? The Barnes-Hatt algorithm. And it should be relatively straightforward. So let's see what happens from there. Now, what have we done so far? So far, we've just implemented the Kuromoto Oscillator to get the guy, well, basically dancing at the right frequency. Now what we have to do is actually move everyone, such that they are now being forced away from our main character. Now, let's go ahead and explain what the Verlet algorithm is. New page before. Give me just 1 second to look it up in my notebook to make sure I don't say something stupid. Okay, here's my notebook. So the Verlet algorithm, we used again a couple times on this stream, and it's relatively straightforward. So let me just go ahead and find it real quick. You'll probably hear me flipping through some pages back here. That's because I'm flipping through some pages back here, so I'd be surprised if you didn't hear it. But again, guys, if you have any questions, comments, concerns, let me know, and we can totally talk about that as soon as I see them in chat. Thanks again, guys, for coming in. And let me see, where is it? I know it's in here. Implementation of FFT, Vitter algorithm. Oh, which we never finished, did we? Visualization 4+ dimensions. Never did that one either. Huh, lots of simulations in here we never did. 1 second, let me just see. This is the Runge-Kutta method. This is not what I want. I want the Verlet algorithm, because it's easier. Creating OpenGL sphere. Nope. Screwed up on that one. What is that title? Yes, so here, this is the Verlet algorithm. Okay. So here's what we got. We are going to do the following. So this is, that is it. If you haven't been here before, for the past few simulations, I guess just the last simulation, we've been basically teaching Steve right here. This is Steve, this guy right here, how to dance by throwing him into the middle of a dance floor. And then he basically follows what's known as a Kuromoto Oscillator in order to dance to the same frequency of everyone else. And now we're implementing the rest of the algorithm, which basically propels or repels people if Steve is dancing incorrectly, and it attracts them to Steve if he's dancing correctly. So it's basically just a force integration scheme based on how well Steve is doing in the middle of the dance floor. Okay, now, what is the Verlet algorithm? Let's go ahead and do here, and let's say Verlet algorithm. Okay, so this is how it works. We do a third order Taylor expansion. So let's go ahead and say x is going to be equal to x naught plus v naught t plus 1/2, 1 second, a t squared. Okay, so that's basically what you have here. We have x, whatever our position is going to be equal to some initial position plus some velocity times time plus some acceleration times time squared plus 1/6 some sort of acceleration, which I think they call b t cubed. Okay, so this term you don't typically see, but it's basically all in here, right? I mean, this is just a higher order term for the Taylor expansion of our kinematic equation, which I feel like a lot of people should know. So now, what we're going to do is we're going to assume that we're moving at discrete time steps. So r, oh, that was an f, r, or let's put x, just to make this more consistent. We're going to say x at t plus delta t is going to be equal to x at t plus v, 1 second, v times delta t plus 1/2 a times delta t, 1 second, squared. Then we do plus, let's see if I can fit this in here, 1/6 b delta t cubed. Okay, then we have x at t minus delta t is going to be equal to x of t, whatever it is at that time step, minus v of delta t plus 1/2 a delta t squared. Okay, and then plus or rather minus 1/6 b delta t cubed. Now obviously we have a difference in sign here, minus plus minus, because this minus is in here, right? So if we square a negative delta t, we get a positive. So this means that this guy and this guy cancel out, this guy and this guy cancel out, and we're left with x at t plus delta t is going to be equal to the following. Just so that we have everything clear, it should be x at the previous time step, so this is going to be t minus delta t, which is great because we do have that one. I'm sorry. It should be, let me get this right. 2 times x of delta t. Okay. And I guess I don't need this extra parentheses here. 2x delta t. And let me just rewrite this over here real quick, just to make sure we have enough room for everything. Sorry about that, guys. 1 second. So we're going to say x of t plus delta t, which is the one we're looking for, is going to be equal to x. Gosh darn it. 2x of t. There we go. Plus a times delta t squared. There we go, because the 1/2 plus 1/2 equals 1. Plus something that is on the order of, 1 second, delta t to the 5th. Then we need to subtract out, then we need to subtract out x of t minus delta t. So we have the current position. Oh, here, let's circle these in red. We have the current position, the previous position, the acceleration, and that's it. So you'll note that in the code I gave it a velocity too. This is because I was thinking about also using the Runge-Kutta method, but for now I think it's okay to just use the Verlet algorithm. It should be okay. I mean, there's no reason to do super hardcore forced integration here, and even then the Runge-Kutta method is not that much better. It's a little bit better, but not that much better. So this is basically what we're going to do, guys. We already have Steve being his awkward self and dancing in the middle of the dance floor and somehow matching the frequency of everyone else, so he gets better and better at the dancing. Now we basically have to repel people for, well, I don't know, when he's not dancing well. And that's what we got. And then this algorithm is done. We'll just do some visualization, put it up on YouTube, and that'll be that. One thing I have to mention, guys, is next week I will be in China for a conference, so I will not be able to stream next week pretty much at all. I apologize for that, which is why I'm going to try to get a video out this weekend for my YouTube channel. And then I'll just be traveling next week, and I should be back the week after that. Again, though, I've been having a lot of trouble getting up in the morning just because I've been working super late lately. And so if it ends up being that I am late to stream, I apologize for that. Like, the thing is, streaming has to come second to work. And one more thing I have to mention. I said that I would stream this weekend, and I fully intended to do so, but things happened. I kind of ran out of time to work on a whole bunch of things on the side. Again, I wasn't able to get up in the morning because I was sleeping, or I couldn't get to bed until super late. And as you can probably tell, I couldn't get to bed until super late last night either. So I don't know. I'm a little bit out of it today too, but that's okay. The way it happens is the more I get up in the morning, the more I stream, the more consistent my streams are. So what else do I have to say? One thing is, I will have to be working a little bit harder at, well, actual work, which is something, well, that happens sometimes. I figure everyone knows how that goes. Simply because as of yesterday, something happened that is good and bad at the same time. So let's, I guess, start with the kind of weird news. I'm kind of kicking myself because of this. So a few months ago, I was writing my thesis proposal, and as you guys know, or if you guys were here, I did not stream during that time because I was just too focused on work, and I just didn't have time. I really had to get that done, and I was really focusing on getting it done. So I was doing that, and what ended up happening was somewhere in the middle of that, I was told to make a JSPS an application to a rather interesting grant here in Japan. So I did so, right? I applied to the grant. However, I wrote a really crappy proposal. I basically just threw something in there. I didn't have any figures. I didn't have any equations. I just wrote random nonsense and I just threw it in. Because people don't typically get JSPS grants. or rather, that was my assumption, that I just wouldn't get it because I didn't have really, I mean, I only have one publication out, and I just wasn't anticipating getting the grant. So then what ended up happening was yesterday, I was sent an email saying that I was brought in for interviews. Now, that's good. However, had I written an actual proposal, I have a feeling like I would have actually gotten the grant flat out, because there's two categories. One category is where you just get the grant, and you don't have to worry about, doing the extra interview. And the other category is where you have to do an extra interview. And then the last category is where you don't get it at all, which is the majority of cases. So, I guess my point is, I now have to go to mainland Japan to do a presentation, or like just a quick 10-minute interview to see if I can get the JS or the fellowship or not. And yeah, the big problem is this conversation is meant to be entirely in Japanese, which I know nothing of. So I now need to learn a lot of Japanese and do a lot of, I don't know, I have a lot of stuff I need to do this upcoming month. So as much as I hate to say it, stream quality will probably go down, which is a direct opposite of what I've been wanting to do lately, but I felt like I needed to let you guys know exactly that. Anyway, guys, at this point, I'm just going to go ahead and pop this over to the next desktop, take this, pop it over there, and then we can go ahead and get started after I get a quick sip of water, and then we'll be good to go. Again, guys, if you have any questions, comments, concerns, let me know, and I will totally talk about it as soon as I see it in chat. Oh, also, one more thing. If you guys see any flickering on my stream, and you'll see the flickering when it's up. So here, let me just see real quick. If you guys see any flickering on my stream, there's one thing you can do to stop the flickering, and that is put the stream on source. The other thing that you should do, if you do see the stream flickering, I don't think you should, but if you do, please go ahead and put that on, report that. Let them know that there is stream flickering, because there's nothing I can really do about it on my side. From OBS's perspective, Open Broadcaster System, what I'm using to do the recording, it's not seeing any flickering, it's fine. But when it's brought to Twitch and it is put on medium quality, which is a quality most people watch it on, then there is an issue. Or really any quality, high quality, low quality, medium quality, middle of the road quality, all these guys, those qualities are all causing screen flickering, and I'm not exactly sure why. So I tried to do a small stream here and there, and again, that was actually why I couldn't get up on Saturday morning, because I was up until midnight trying to fix that. Anyway, just lots of weird things. So let's go ahead and get started. Let's CD into projects, Simuleos, and of course, Kuromoto. And we go over here, CD projects, Simuleos, and Kuromoto. Okay, from at this point, I do not have a makefile really ready. However, we have one in this directory, so let me go ahead and open up makefile. And let's just go ahead and get it set. So I'm going to remove these flags. And let's see, what do we have here? March native, F OpenMP. Yeah, sure, this should be okay. I don't think we're really going to be using OpenMP for this. Hey, happy little rat. But that's okay. This is basically the makefile from the geometrical optics. So let's go ahead and just reset it up for the how to dance simulation. And then we'll go from there. So, how to dance. There we go. Objects, how to dance.o. To dance.o. Looks good to me. Object visualization.o we don't have, but we probably will have something like how to dance visualization a little bit later. Geometrical.h, again, we don't have these. So that should be okay to just go ahead and maybe set that equal to nothing. I don't know how that's going to work, but we'll try it. Okay, so now we have this. Let's see, /geometrical. Nope, that's not what we want. We want how to dance. There we go. Right, quit. Make. Okay, seems to work okay. So, what is this actually doing? Let's go into the code real quick. And actually, I just realized we have a whole bunch of warnings. Let's go ahead and fix those first. So, we go into how to dance. Oh, that was the executable. We go to how to dance.cpp. There we go. Okay, so let's go ahead and fix these warnings. The first one is 23. And it says, warning, oscillator freq will be initialized after order. Will it? Let me see. Wait. Phase. 1 second. We initialize here. Okay, so we have oscillator. Position, velocity, acceleration, freq, and phase. Yep, so let's go ahead and put the phase and freq in the appropriate order. because they are in the appropriate order on the other side. So let's go here, and then we'll add freak at the end. There we go. Okay, so now if we run it one more time, those warnings are gone. And now let's go ahead and talk about what's happening here. Basically, I am creating an oscillator, a vector of oscillators, and this vector of oscillators is going to be the initial group that Steve is in, right? So it's going to be the group of dancers that are originally doing their dancing, right? So we initialize the group, we say, I think there are 20 members, and then I just set everything to 20. So I said their frequency is 20, the dance floor size is 20, so on and so forth. Then I said Steve. Steve is going to have some sort of random phase, and he's going to have a maximum frequency that we allow. And that's basically what we have him start at. So he has some sort of phase and some sort of frequency, and he just starts dancing. And then he eventually synchronizes with the group. So here's us synchronizing Steve with the group. Now, there's one thing we have to do at the end of synchronize, and that is I want to set Steve's natural phase, or natural frequency, to be the frequency that he gets at the end of the simulation. So we say Steve.frequency is equal to his natural frequency. And so we're constantly changing Steve's frequency. So this means that at the end of the dance, he is naturally dancing with everyone else, which is great, because if he's naturally dancing with everyone else, this now means that if we change the song or anything like that, we'll see everyone be repelled again, which is kind of what we want to see. So, what are we going to do now? What we need to do now is, well, put in the force integration stuff. So now we have the positions of all the characters. Let me go into what an oscillator actually is. And it's up here in struct. So we have position, velocity, acceleration, and phase. And actually, guys, I can remove the velocity because the Verlet algorithm is only dependent on the position and the acceleration. So let me go ahead and remove the velocity now. However, let me think. Do I need it for anything? If we add in a force that is like some sort of drag force, we might need it. Hey, Flood from Nowhere, what's up? So we're going to remove velocity here, and we're going to remove it over here too. There we go. Of course, we got to remove it here, and down here also. And there we go. Velocity is out. So what do we need next? Well, we need a couple of different guys. So let's go ahead and move down here. Your streams always put me in a good mood. I'm glad. Okay, so now what are we going to do? We have Steve dancing. I mentioned we're going to need the Verlet algorithm. So let's go ahead and do void Verlet. Okay. Now, what we're going to assume here is that Steve is not going to move. He's going to be in the middle of the dance floor dancing, but no one, he's just going to always just awkwardly sit there in the middle of the dance floor. So what we need to put in here then is std vector of oscillators. And this is just going to be group. And they will be changing their, I guess, position every time step, which is the other thing we need to read in double DT. Okay, looks good to me. So I guess we'll just go ahead and put this in there. So then we're going to say function to calculate change in position. Now, one thing I want to point out, guys, I'm going to pop it up over here in the left terminal. This is a little bit different than what we were doing before, but not that much different, right? So let me go ahead and open up, let's see, what would it be? Barnes Hut, I believe. I guess capital V, because I'm great with naming things. Barnes Hut.cpp. Let me go down to Verlet. Okay, so before we have done this Verlet algorithm in a little bit of a more complicated case. Gosh, darn it, I can't speak. So we say, like, the vector's temporary position is going to be equal to, whatever position is before, and basically we just do this. We say it changes with time, right? Now, one thing I have to point out is we have consistently found the acceleration every time step, every time, right? So what we've been doing is we have been updating the acceleration every time step for all the particles with another force up here. And this is what's been allowing us to get our accurate results. So what we have to do first is we have to actually search through and change the acceleration of all the particles. And this is something I just want to point out. The Verlet algorithm itself, right down here, does not necessarily have a dependence, or rather, if we have a constant acceleration, will work perfectly fine. But because our acceleration is changing, we do need to change that acceleration and go from there. So let's just go ahead and recreate this Verlet algorithm. Again, it's just right over there, so should be relatively straightforward. So let me go back up to the top, grab our comment, and now let's pop down here. I don't know, guys. I don't know. As I mentioned before, I'll be heading to China next week, and I just gotta get a lot of work done before then. But I also really need to get a video out. Gosh, it drives me nuts how long it takes for me to get videos out. And yeah, sure, I realize maybe people are okay with that. Maybe they're okay with me getting a video out every 3 weeks or a month, but I'm not really okay with that myself. You know, I feel like if people are subscribed to me on YouTube or something, they want to see my content. And if I can't get the content out regularly enough, I mean, why, I don't know, why subscribe in the first place type of thing. Hey, Gustward, what's up? So here's what we're going to do. We're going to say, what are we going to say? We need a position P, but luckily that's just going to be an X. So we're going to say double temp X. What was that? Temp X. We're going to set this equal to the previous position P. So what we probably should do is, wait, what am I doing up here? Why am I calling this that way? It should be okay. We'll see what happens. So let me just go ahead and right put here. And now we're just going to say we need to go through all the people. So we're going to say searching through all dancers. And I guess, how about changing the position? Oh, come on. Position of all dancers in simulation. There we go. So here's what we're going to do. We already have temp X, so let's go here. Let's say for int I size t I equals 0. Then we say I less than, what do we have here? Group dot size. Then we do I plus plus. Gosh darn it. 1 second. Group dot size. Now let's go down here. And let's pop down here. Oh, sorry about that. There we go. Okay, so now we're going to do double temp X. This is going to be the X position of whichever group member we're working with. And of course, we could do another for loop. This is just the one that I went ahead and went with. It could be auto, I, whatever. So we're going to do temp X. And we're going to set this equal to group. Oh, 1 second. Group of I dot position. And I think I just called it dot position. Okay, so now for the actual relay algorithm, we're going to say group of I dot position is going to be equal to, let me go up real quick just to make sure I have the position correct. Yes, I did call it dot position. Okay, so this is going to be equal to what we just had up before. It will be 2 times its current position, so we'll say 2 times its current position, so we'll say group dot of I dot position. And actually, guys, just because we are going to probably run out of room with this particular line, let me go ahead and change this loop up. So we're going to say for auto, I guess we're going to say group member, but using int in a for loop is actually better. Oh, really? Interesting. Well, anyway, I'm changing the loop up anyway. So we're going to say group member. Sure, this should be okay. In group, I guess. Yeah, I guess that's okay. And then we're going to say double temp X is equal to group dot position. I guess member dot position. And then we're going to say group member dot position is going to be 2 times member dot position. Okay, so what are we going to do next? 2 times member times dot position. There we go. Subtracting out. Let me remove this line up here. What do we want here? Subtracting out should be the previous position, which is going to be equal to, let me see, should be member dot previous P, I believe. Oh, thanks for the ampersand. I totally forgot. Totally forgot. Thanks. 1 second. Going up to the top. What did I call it before? Double position, acceleration. Oh, shoot. Even though I removed the velocity, I'm going to have to add in the previous position. That's a bit of a pain. Okay, so let's add in the previous position. So we're going to say PPOS, previous position maybe? That should be okay. So let's go here. And let's set it naturally equal to 0.0. And let's see, double P. And I guess we're going to say double PP. And PP. That was an awful naming scheme. I'll change it in a second. Let me go down here and let's say member.previous position. For now, I'll just keep it PPOS and go from there. So member.previous position. Now what's next? Next, we have to add in the acceleration times dt. Now, one thing I have to point out, the previous position is already going to be 1 time step below. However, the acceleration is just dependent on the change in time. So this is going to be interesting that we have to actually multiply the acceleration times the time step squared. So now we're going to add in the member dot acceleration times dt times dt. Now what we do at the end is we say member dot previous position is going to be equal to, hey, that's your fan, what's up? Temp x. And now we should be good. So, dang it. Okay, so if the screen is flickering, guys, there isn't much I can do about that. The only way to fix that is you go to options and bring it up to source. That's the only way I can currently figure out how to fix it. I spent literally hours trying to figure out how to fix it. No, it's fine on my side. On my side, the screen flicker is not there. It's only when it's brought up to Twitch and people are using source or non-source viewing options. No, I keep my bitrate rather low, so it's not something that, like, again, if I take the direct video stream from OBS, there is absolutely no flicker. However, when I, let me see 1 second, is it on source? Yeah. However, when I put it up on Twitch, for some reason, if I'm using Medium or anything, it just doesn't like it. I can't figure out why. I've sent in a message on like Reddit or whatever. I said, hey, I don't know what's happening. No one else seems to be having the issue. So one thing I'd like for you guys to do is, if you guys have that issue, could you please go and just report the playback issue? Video stutters, audio is fine. That would be super helpful, because I mean, I can't do anything about it. I've already put in kind of everything I could, and I guess I will submit another message to like technical support or something like that again later today, because honestly the flickering makes the stream almost unwatchable, and there isn't really much I can do about it. Hopefully when I get back from China next week, it should be okay. Yeah, I have no idea what the problem is, so if you guys have a suggestion on how to fix it, please let me know, because I am racking my mind, and I can't think of anything there. So, oh, there's no way to select the, ooh, well, nothing we can do about that one, is there? Okay, so, now we go up. Oh. So, we have synchronize, we have relay, so let's go ahead and add in another function here, which is void find acceleration. Okay, and again, guys, I'm not claiming that this is the most efficient thing, but it'll get the job done. So we're going to say std vector of oscillator. Then we say this is of group. There we go. I'm watching a mobile, and you can select the quality. Oh, the problem I noticed with high kilobytes per second spikes. Maybe, but so maybe that's the issue with OBS. It could be that OBS is just sending too much information too quickly, or something like that. I'm not sure. I have no idea what the issue is, but I do know that on source it is fine. I know that. So that is a very quick fix to things while we're currently figuring out how to get the screen flicker away. And again, if you guys have ideas, if you guys have ideas, please let me know. Because again, I tried a number of different things, and just for the record, you'll see a few streams where I was trying to play a video game, Guild Wars was what it was, to see if I could get rid of the screen flicker, and I couldn't replicate it there. However, for some reason when I'm doing my programming streams, which again I have a lower bitrate for, and maybe that's the issue, it's doing the flicker. So I have no idea how to fix it. Anyway, that's beside the point. If you're watching this on YouTube, I'm sorry. That was a long conversation for something that you guys do not see. Okay, so let me see. Group. And what else do we need? We need to find the acceleration, but I think that's all we need to do, right? Because the acceleration is going to be dependent on everything else. So let's go ahead and figure out what the acceleration is. So let me go ahead and pull up Zernal. Here we have our equation that we've done so far, page, new page before. Now, as I said before, the force I want to work with on my end is going to be a function of r, not 1 over r squared. So we want to say force, let's put in black, is going to be equal to, again, the attractiveness of Steve times the, yeah, actually, we do have CVR. That's your fan. I meant I put the recordings on YouTube later, so if people are watching it. Yeah, I'm definitely using CVR for that. I can show you guys the settings that I'm using if you need. But I don't know what I can do to fix it. I tried a whole bunch of different options. Anyway, so we're going to say the force of attractiveness of Steve and the desire for our particular member to be accepted, kind of like GMM times the 2 M's. And then we may have some sort of constant out front, but that's okay. We'll multiply this by some sort of constant, and then we want this to be a function multiplied by r. And again, the reason we want r in the numerator and not denominator, hey, that's your fan. You were here earlier though, right? Here you are, right here. So the reason I want it in the numerator and not the denominator is because it works a little bit differently. To switch except VBR, I don't see why they shouldn't if they set the max to 350p. 35,000 or 3,500p. They do have variable bitrate, and I could try variable bitrate. I did though, and it seemed to not change anything. But again, I could try variable bitrate again. Just make sure you saw. Oh yeah, I definitely saw. Sorry if I didn't say hey last time. Okay, so we have C times AA times R. And again, this means that the further away the characters are, the higher force they'll feel, and the closer they are to Steve, the less force they'll feel. And so we'll have this kind of movement of the characters where the closer they are to our awkward dancer, the less of a force they feel. And this should be okay, right? Because this means that, like... Oh, wait a minute. I gotta think a little bit more about this one. Okay. What if we have a repulsive force instead of an attractive force? Okay, if we have a repulsive force, we might need to think about this a little bit differently. So if it's attractive, let's change this. So if it's attractive, this is what we have. If it is repulsive, then we have this equal to CAA over R squared. There we go, now we're set. Is recommended settings to avoid TCP piping problems. Yeah, fair enough, I guess. Okay, so this is what we have. We have to split it up into two categories, F repulsive and F attractive. So basically then what we need to do is in our acceleration plan, we need to read in some sort of cutoff that allows us to move between the two. I think this should be okay. I find the whole idea of TCP for time sensitive data absurd. What exactly is TCP? Sorry about that. Again, I don't really know much about encoding either, so... Okay, so what do we have here? Force repulsive, and I'm sorry, you guys have to realize I'm a complete noob to a lot of this kind of stuff. This is what we want to do for forces. So again, both of these guys are going to be equal to mass times acceleration. So our acceleration is going to be equal to the following. So in the case of an attractive force, it will be, well, basically force attractive over mass, or force repulsive. Repulsive over mass. Okay, so this is where we're going to have to kind of, I guess, mess around with some settings. This was meant to be a semicolon, not a J. There we go, it still looks like a J. Transfer control protocol. Oh, yeah. Reliable transfer protocol over IP. Thanks, guys. Let me see, what do we have here? Especially for live streams. Yeah, so I don't know so much about it. I wish I did, but I just don't. Okay, so now we have these two characters here. And guys, we're going to have to play around with the numbers a little bit to make sure we don't have crazy oscillations or anything going on. But that should be okay, right? So we'll just kind of plot that out with new plot, and basically we'll spend a good bit of time today matching everything. Okay, so now let me think. What we need, do we actually care about having individuals with different acceleration, like with different accelerations? I feel like it's okay for them all to be equally attracted to Steve and equally repulsed by Steve. So let's go ahead and do one more last make, just to make sure I didn't screw anything up. Let me actually write this first and then go over here and run make. And it looks like it's all still running just fine. Guarantees that you'll receive packets as they were sent. Yeah, well, obviously we're not seeing packets as they're sent. Well, I don't know. Maybe we are. I don't know. Let me get a quick sip of water and then we'll continue. Mm. Yeah, so again, it's just so weird that putting it on source fixes things. Okay, so now what I'm going to do is go over here and I'm going to add in a somewhat arbitrary cutoff. So we're going to say double cutoff. Okay, so what we're going to have to do is find the maximum and minimum of a couple different guys to figure out what this cutoff value is going to be. But for now, let's go ahead and go in here and find acceleration of all dancers on the dance floor. Okay. With different protocols, you can just discard some packets. Doesn't H.264 screw up if you don't receive certain frames though? Maybe. I might be using that to encode, because I do certainly use MP4 files for a lot of things, so I might have just picked that one because I recognized it. What's the different protocols? You can discard some packets. Yeah. You'll have artifacts until next keyframe. Yeah, so it could be something on my side. I just don't know what I need to do to fix it. So, and it's not, people are not always having that problem. It seems to be only my stream and a few other streams. And again, guys, if you're just popping in and you see screen flickering, just go to source. It'll fix it. Okay, so let's go ahead and pop this down to the bottom, finding acceleration. And let me also do one more thing. So let's go here. And let me say up here, if, let me see. So you're going to have artifacts every time if you have packet loss. What is this? Magpie. Open link. Hello, would you like to hear a TCP joke? Yes, I'd like to hear a TCP joke. Okay, tell you a TCP joke. I'll hear a TCP joke. Are you ready to hear a TCP joke? Yeah, I'm ready to hear a TCP joke. Okay, I'm about to send a TCP joke. It'll last 10 seconds. It's 2 characters, and it does not have a setting. It ends with a punchline. I'm ready to hear the TCP joke. I'm sorry, your connection is timed out. Hello, would you like to hear a TCP joke? Packet loss isn't very common anymore. It was common with modems, not with broadband. Fair enough. Okay, so what I want to do, guys, is I want to say if all of our characters are, like, I don't know, at the end of the dance floor, then they're at the end of the dance floor. Like, they can only go so far. So we're just going to repel them all basically to the edge of the dance floor. And what does that mean? That means if their position, let's do this. So we're going to say if member dot position is greater than, let me see, we'll say 10 because that's the size of the dance floor. So we'll say the absolute value of member dot position. No, we'll just do, I'd rather have corruption until the next keyframe. Yeah, I don't know. Anyway, so we're going to say if member dot position is greater than 10, we're going to say the following. Member dot position is going to be equal to 10. And the reason we're doing this, guys, is just because he can't really get over that size. I mean, that's the size of the dance floor, right? And then we're going to say member dot position, where are we here? Dot position is less than 10. We're going to say member dot position is equal to 10. Now this is obviously going to give us a bit of a problem in that once everyone is forced at the edge of the dance floor, they're all going to be at the same position, which means that as they're going to be attracted to Steve a little while later, they're all going to be basically forced together at different speeds. So we need something, or at the same speed. We want them to kind of come together at different speeds so you can actually see the difference between the different dancers. That's kind of important. We'll add that in just a second. So let me go ahead and put in a quick note at the very top, just so I don't forget it. Let's go here. I'm missing a few things, but I'm kind of keeping up with chat. So now what are we going to say? We're going to say, note, add in different constants. 1 second. For different dancers. This basically means that we can see all of the dancers individually coming towards Steve, and that should be okay. Yep, that should be good. Okay, so now let's go down to the bottom and let's do our find acceleration command. So we're here. Let's go ahead and pop down here. The acceleration should be relatively straightforward. So this is what we're going to do. We have the cutoff there, and we say if. Now let me think. We have Steve. We should probably read him in 2. Yeah, we should totally read Steve in 2. So we're going to go here, and we're going to say oscillator Steve. Okay, and let's pop up and put that up on the top. Another can of worms, and start talking about details on those. Yeah, I mean, this isn't... The truth is, I know that it's not a particularly easy problem to solve, right? 1 second. Oh, come on. Tor. Steve. Okay. UDP will be more efficient and can at least select no modes of failure, unlike TCP, that can, in the worst case, stall for seconds. Yeah, okay, I can add an ampersand to that one. Yep. Let's go here. And let's add it down there too. Okay, yes, should be good. Good. Okay, so now what we're gonna say, if, okay. 1 second, checking. How far off Steve is. Okay, so here's the thing. Let me see. We have some sort of natural frequency of Steve, right? He's naturally wanting to go at this speed, but everyone else is going at this speed, you know? They're moving a little bit faster. So if we have Steve naturally moving at some frequency, let me go up and see how we're doing this. So we have, let me see here. We have this entire simulation where he is slowly but surely matching the speed of everyone else. So in this loop up here where he is slowly becoming at the same acceleration as everyone else, we should probably do the simulation here, in that loop. So it should be okay, I say, to do the following. So we'll say if Steve dot, let me see, if Steve dot, what was it, frequency? Yes, minus, what do we want? We want group member dot frequency. So let's see how far off Steve is. Yeah, so we'll do the following. So for auto member, again, ampersand. And what do I want here? Member in group. 1 second. Gosh, I cannot type today at all, but I guess it's part of the course. And then we're going to say Steve frequency minus member dot frequency. And again, they're all dancing at the same frequency, so it should be okay. Steve.frequency, member.frequency, and then we're going to say is less than cutoff. So that means, let me see. If Steve, this is going to be an attractive force. Okay. Cutoff. Let me go down here. And now we're going to say repulsive force. And it's just going to be an else. Okay, so now we have the positions to put in our attractive and repulsive forces. While I advocate UDP clear reasons, HPG can be over anything. Yeah, man, you guys are all talking way over my head though. I don't know very much about these protocols and such. 1 second. I had to clear my throat. I'm gonna get some water too. For some reason my voice is getting all raspy. Okay, so let's keep going. We have Steve. Did I capitalize Steve's name anywhere else? I don't think so. Anyway, let's go ahead and do it. We have the repulsive force and the attractive force. As I said before, I want the attractive force to be relatively straightforward. So here's what we're going to do. HTTP assumes a reliable transfer protocol though. Maybe. Okay, so what are we going to say? We will say the member.acceleration is going to be equal to, what do we want? We want the force of attraction over its mass. Now let me think. Do we have a mass? Go to the oscillator. Position, acceleration, phase, frequency. No, we do not have a mass. So we'll just assume the mass is all the same, which is going to be equal to 1. Then we'll just kind of say... Sorry about that. My throat is just killing me. Okay, so now we're going to say what? Let me see. So acceleration times time. That's kind of what we're dealing with here. So what kind of acceleration do we want? I suppose we could put in an acceleration, a standard acceleration of, let's say, maybe 10. And then we'll divide that by r squared, how far away we are from Steve's position. And that should be okay. So we'll do that. So we will say just some arbitrary double for now. And that's something that we need to fix. But again, some arbitrary double. And then we're going to divide that by r squared. Because again, it's for example, GMM over r squared. Or I wrote CAA over r squared. But those are all just constants, right? We can't change those. The r squared is the big guy here. So we're going to do... let's go up here. And let's just go ahead and... yeah, let's go ahead and define it. So we'll go up here and we will define... since we're going to need r for both of these guys, let's just go ahead and define the change in position. So we'll say, I don't know, delta, let's say x diff. There we go. And we go up here and define x diff. So we'll do double x diff, semicolon there. And we'll say x diff is going to be equal to member dot position minus Steve dot position. Okay. Now, let me see. I forgot an equal sign. Auto ampersand. What did I forget? No, I have an ampersand there. Should be okay. So equals there. By the way, hey Gatex, in case I missed you, and Semyon and TS Jost, thanks for coming in, guys. I apologize. You guys were in there for a while. I just kind of didn't say hey. Okay, so we have x diff is equal to member dot position minus Steve dot position. Now let me think here. We should probably... oh, it's fine. It's fine. This will be fine. Yeah, it's okay. Let's do x diff times x diff. Okay. Now let's go down here, and for the repulsive force, let's think about what we need to do. We need to say member dot acceleration is going to be equal to, again, some sort of random constant, but this time it's going to be times x diff. Okay, so let me just make sure we got this. Oh, I see. How does auto resolve ambiguities? You know, it kind of depends. So personally, I kind of like the other loop better. I like when we do for int I equals whatever, you know, and you kind of explicitly type I. However, in cases where I don't need I'll get rid of it. It's fine. It kind of just depends. Okay, so what do we have here? We have member acceleration times auto x equals 4. Yeah, I mean, that's fair, right? So I guess instead of auto, I could put oscillator, right? That's fine. Okay, let me think. What do we have? If Steve.frequency, member.frequency. Okay, so in the case of our attractive force, I did this backwards. I totally did this backwards. Crap. Okay, let me just do this. I'm gonna change this to a greater than sign. And this is gonna be repulsive force. Sorry about that. There we go. And this is gonna be attractive force. Oh, I can't spell repulsive either. Okay, so there's our attractive force. There's our repulsive force. Repulsive. C roots. Okay. Good. So let's move from there. Steve.frequency minus member.frequency. Here's the cutoff. I'm gonna put an extra set of parentheses around here just to be explicit about it. It'll be fine. I mean, obviously there's no problem, but I like having an extra set of parentheses. Okay, so now let's check this x diff guy. So let's say Steve's position is going to be equal to 0. That in the member position is going to be equal to a positive number, right? So if Steve's position is equal to 0, the member position is positive. That means the acceleration is in the positive direction, so that is good. Okay, so we just checked. I think everything should be okay. So let's go ahead and see what we need to do for this stuff. We need to find the acceleration. Then we need to have the relay algorithm here. And now I just need one more function in here to update everything. And I guess I could just put this all into the relay algorithm. Want long? Had a good sleep? Okay, so let me go up to the top real quick. What are we going to do? We are now going to have one more function. And this function is to, I guess, update the positions. So we'll say function to update all member positions. Okay, so we're going to say void update positions. I guess we'll just do pose of std vector of oscillator, and we'll do ampersand group. And that should be okay. We have all this, and let me see, what else do we need? I suppose we also need Steve, so we'll do std vector. Oh, he's just an oscillator. Steve. What else do we need? We need cutoff and DT. So I guess I'll go ahead and put these down here. Double cutoff and double DT. The order doesn't really matter too much. Long, include, and monstrosity that is declared type auto. Okay, update position. SE vector oscillator group, oscillator Steve, double cutoff, double DT. And literally all this is going to do is find the acceleration and then do the Verlet algorithm. You know what? We don't need this. We already have that synchronize function, right? So let's just go down to the synchronize function. Here we are there, and here we are here. And let me see, do we have everything in the synchronize function that we want? We have DT, we have oscillator Steve, and I guess what we need to do then is read in the stuff from there. No, actually, I am not writing any type of physics engine. I'm just kind of having fun with simulations. This stream, the way I see it, if you want to watch someone making a physics engine or something like that, there are other people who can do that here. What I'm doing is just kind of going through random simulations that I find interesting. Today we're kind of going through the Kuromoto Oscillator, just kind of synchronizing stuff, and I just decided to do a silly example of some guy learning to dance. And I just kind of wanted to see how we can relate the oscillator to basically the movement of different people. So we could maybe use some sort of optimization strategies on that a little bit later, but for now, I just kind of wanted to set the idea in motion. So we have init Steve, and what are we doing here? We have synchronize. Let me go ahead and add in synchronize one more guy, and this is going to be double cutoff. Go here, DT. Now, what are the cutoffs going to be? Let me think. So it's going to be a change in the frequencies, right? So what is the highest frequency we can get? The highest one we can get is 20, right? So if the highest frequency we can get is 20, that means the cutoff we'll say is 10 for now, and then we'll see what happens. So we avoid synchronize. Where do we use synchronize? Here it is. So we have 0.1 for the time step, and let's do 10 for this guy. Okay, so this means that all the positions should be updating. Now, are we outputting anything yet? No, I don't believe we are. So what do I want to do then? I'm not sure if it would be possible to watch someone write a physics engine, because people who are able to write proper physics engines are cray-cray. Wait, what do you mean cray-cray? I feel like, I don't know. I mean, we don't do anything particularly complicated on this channel, but every once in a while, the physics is quite hard to cover. So let's do synchronize here. Now, one more thing we probably want to read in. I think one of the standards will add auto parameters for functions. Okay, so one thing I also want to add into synchronize is the following. I want to add in, let's see, std, I guess it's going to be upstream, and let's do file. And let's go here, add in two of these guys, and let's also add in a ampersand, because otherwise I don't think it'll run. Okay, so let me go up here, make sure fstream is read in, and now let's go to synchronize. And let's go ahead and call it appropriately. In fact, let me just go ahead and do this here. And let's go down to the synchronize function down here. Yes, and let's change the call. So we're going to go here and we're going to say, what did I add in? I think it was double cutoff. And std of stream file. Right here. And let's go over here to G++. Where's the last G++? Somewhere in here. Okay, maybe not. 1 second. Let's do G++ with an exclamation mark. Okay, that one seemed to work just fine, but I think I forgot to write. Let's try it again. Okay, worked just fine. I'm using auto heavily in my own scripting language. It was fun to implement. Yeah, I can imagine it's actually probably a pain to implement, but that's okay. So we have the cutoff, we have the file. Good. Okay, so everything seems to be going okay. So let me go up to synchronize. And I guess we just need to open the file appropriately. So let me go up to main. And guys, I have to apologize every single time I use fstream. I totally forget how to open files and stuff like that. I realize I should know by now, but I always forget every time. So it's something I'm going to have to look at old code for. Again, I definitely apologize. Okay, so here's what we're going to do. There we go. That's what I need. STD of stream. What do we want? We want particle output. That's okay. We'll do particle output too. Well, we only have the one file, so let's just do file. Okay. Good. Is that all I need to do? Oh, and then I also have to say, and the file's name is going to be particle output. One second, particle output. Oh, come on, put. Where's the T? There we go, dot dat. And then we're going to do std of stream. Yep, and then we want out. And that should be it. So now we just read that in, and of course at the very end we have to be sure to close it, and that will be done with file.close. And now let's read file in here. And let's do a make command. Error, forgot semicolon. Where did I forget the semicolon? Oh, it's right there. Do it again. There we go. Seem to run too. Good. What did I miss? I always wanted to know, why do functions have such a horrible syntax? They throw the identifier right at the middle where you would least expect it. I guess you just get used to it, right? Let me see. So what do you mean by function? So do you mean these guys right here, the function initialization guy? What is this called? I guess the tag? I'm not sure. Community wanted to use reserved keywords. Impossible without breaking existing code bases. I don't know. I mean, the call right here makes sense. So like, for example, this call right here makes a good bit of sense because it follows mathematical notation, right? So you say f of x is a function of f of x, y, z is a function of x, y, z, right? So this makes sense. I'll admit that maybe this call down here is a little bit hard to follow, but in the end, it's still the same thing, right? You're defining this, and you're saying, here's the function for it. So I think it's just because it follows mathematical notation to answer that question, Cadex. So even between the two. But yeah, definitely clarification could be helpful. Let's do sync. Okay, here we have synchronize. Okay, so what do we need to do now? We're going through each of the individual members, so what do we need to do? Well, let me think. We have while. Since we're already going through all the different members, let me change something real quick. So we have the find acceleration command. However, the find acceleration command currently goes through all of the members, and the relay algorithm does too. However, I don't think we need to necessarily do that. So let me go through and let's fix this. So instead of having these depend on std vector, let's just make them have an oscillator member. Let's do the same up here, oscillator member. 1 second. I guess I could have left those functions as they were. It's fine, it's fine. Okay. C++ is commonly mess of incompatible ideas nowadays. Yeah, that could be true. Okay, so instead of going through all the members in the group, we already have member and we have everything there. So let's go ahead and remove some spaces. So we're going to do 4x, and we're just going to pop that down for all these guys. Okay, so what do we have here? We have double temp x, member.position equals 2 times member times acceleration, and we set the position equal to something. Should be okay. Good. Good. Okay, that should be okay. It's impossible for high performance games. Not much for, oh, for Rust, I see. Okay, we're gonna do the same thing down here. So let's go ahead and remove this line down here. And let's go ahead and remove from 4 spaces. So 4x, and remove all these guys down here. Okay, good. So we have xdiff, everything else should be set. Checking out for Stephus, let me go ahead and add in some spaces here, just to make it a little bit more readable. Good, okay, and here's what I'm gonna say. We are forcing, 1 second, dancers to remain on dance floor. Good. Rust isn't high performance. Not sure. So actually, Gustorn has been using Rust a lot. We can write the engine C++ with unsafe hacks, and write game logic in another language. Yeah, I think a lot of people do that, right? I mean, that can't be too terribly uncommon. So the repulsive force, yeah, we have the members all being updated. Let me see, what am I doing wrong here? Member.position. No, I think this should be okay. So let's go up here and let's just perform the relay algorithm and such like that. So first we need to find the acceleration. So Steve.frequency equals natural frequency plus sum. Oh, that should be okay. Now we gotta update the position. So we have this update position guy right here. Let me see, what is this update phase guy doing? Is this update phase guy going through... 1 second. For size t I equals 0, I less than group.size, I plus plus. We're going to say group.phase plus equals group.frequency plus dt. What is this doing? So every single time step... Oh no, guys! Ah, I'm an idiot! We needed to keep them as they were before. Let me just go ahead and quit this, open it up again, down here. Good, so this is how they were before. My apologies, guys. Let me just make it real quick. Jeez, I'm an idiot. Okay, that's okay, though. So, let's go and update the positions. And this is just going to be done with the relay algorithm. Let me see, sum is equal to group 0.phase. And I need to leave a quick note here. Note that sum, the sum, all frequencies of members in the group are the same. Good. Okay, so that's going to be that. That should be okay. Now, after we change Steve's frequency, let's update the positions. Positions for members in the group. What am I missing? LLVM is okay. We'll get better and better as it's a more supported platform. I feel LLVM super supported, isn't it? Like, most people use it, so far as I'm aware. Let me see. Interesting. Okay, so let's pop down here. So the first thing we need to do is, I guess, find everyone's acceleration. So we're going to do find acceleration. And what do we need to read in? We need to read in the group. We need to read in Steve. And we need to read in a cutoff. And then we add in a semicolon there. Now we do the relay algorithm. And we're going to do relay of the following. So we want group and double DT. Okay, good. His position is added in. STD03 string equals STDC out. 1 second. It would be more consistent if you wrote it as STD upstream. Oh, okay, I think I see what you're getting at. You can write a simple toy language with similar C performance to C. Yeah, I mean, to be fair, Julia, for example, is, I think, using LLVM, right? So it's quite useful. C performance comes from allowing programmers to optimize their code better, not really from anything else. Yeah, maybe that's true. I don't really know. I do know that I can... Jeez, it is super hazy outside. Anyway, I know that it's easier for me to write fast C code than it is for me to write fast Julia code, but it's because I know how to write C code and I don't know how to write Julia code. I'm not going to argue I know how to write fast C code, but I do know how to write C code. So that's kind of the issue. I don't know how to get the optimizations out of, for example, Julia, and we should be good to go from there. So let me go ahead and write this, and now all we need to do is output the positions of, let's say, what do we want here? The Rust compile times are terrible. The produced binaries are huge, and the Rust front end leaves a lot of performance on the table. I think Gustron would say Rust is definitely worth getting into. Okay, so what do we want to do then? We have synchronize here, we have the file that we're reading in, so let's just go ahead and output the particle positions here. So we find acceleration, and let's just go ahead and create a new function, which is output positions. So what do we want to do here? What do we need to actually output? We need to output the positions, and we also need to output the phase. So let's do that. Where are we? We need here, new function, to output all positions. Okay, so we're going to do void output position. And this is going to be, what do we want here? We want std vector of oscillator. And let's see, what do we want? We want group, ampersand group. And we're also going to need Steve. 1 second. Then we want oscillator Steve. Okay, now what else do we want? We want Steve. Now we need the last thing, which is kind of important. We want std of stream file. Yes, file. And I think I forgot yes, I forgot an ampersand file. 1 second. Okay, and that should be good to go there. Now let's pop over here and add the ampersand before Steve. Good. Just for hobby products. Okay. Also, the debugging experience for us is bearable on Linux, terrible on Windows. Yeah, that's fair enough. I need to learn debugging. I know how to use GDB now. I just haven't really used it that often, and so I kind of forget. So let's go ahead and pop this down at the bottom. G. Output here. And let's go ahead and put it in here. So what do we need to do? The first thing we want to do is output Steve first. Steve first. So it'll be the first position, and everyone else will be the positions on top of that. Okay, so here's what we're going to do. We're going to say for, rather, std. Wait, what am I doing? We already have the file. Let's just do file. And what do we need to output? We want to do steve.position tab. Then we do steve.phase. Yeah, phase. That's what we want. And then we end the line. Now we do all the other people. Oh, come on. Outputting. I can't type. Yeah. I do a lot of that. C++ is beautiful as far as developer productivity goes, but I see what you're saying. What are we saying? C++ is unbeatable. Oh, I see. Outputting all other peeps. People. Okay, so let's go do, for, auto, ampersand, member, within, group. And then we're gonna do, file. And we're outputting member.position, tab, member.phase. Then we want new line. Good. I'm a Linux, so I'm pretty much forced to do print debugging. I mean, yeah, Qt Creator is, yeah. Okay, so now we should be able to output all the positions, and let's just see if it runs. The worst that happens is it doesn't run. Okay, so we find the accelerations here, relay, and then finally we output the positions right here. Output positions of, and I believe we did group first, then Steve. Let's go here, let's make that. Okay, so we get a whole bunch of errors. Fantastic, I love errors. Let's see, what do we have here? Lots of errors. The best errors. All of these errors. Holy crap, that is a lot of errors. How? Oscillator Steve. Oh. What do we have here? Where are we? We are in synchronized output position. I forgot to add in the file at the end here. Member position. Let me go here. Write this, go here. Let's go ahead and clear a couple times. And now let's do that one more time. Good luck linking. Anything involved native code is terrible on Windows. Good luck linking. Yeah, I don't know. I don't know how to code very well in Windows. I'm not gonna lie. It's not something I can do relatively straightforwardly. Let me see. No match for operator. Did I put those in the wrong order? Holy crap, I did. Dagnabbit, all of them were in the wrong order. That is me forgetting syntax. Man, I haven't done that one in a while. Just goes to show you. I don't know what it shows you, actually. Holy crap. Okay, so we're gonna put this there. There. Man, that one has not popped up in a while. It's actually kind of nice. Okay. Here. Oh. Make. Okay, that one made just fine. Now let me go ahead and do ls. We should have particle output, so let me go ahead and go particle output.dat. Looks like everything's just fine. Now let me see, what do we have here? We are outputting member.position. They're all at 10, which means we're giving them too much force. So let's go up here and let's just do 1.0 divided by the x difference here. Okay, write this, go here. And let's see what happens as we go down a little bit. Down to the bottom. Yeah, okay, so that's clearly wrong. Let's go ahead and do make again. And let's go into particle output.dat. Okay, still all the people are being forced to 10, which makes me feel like maybe I'm doing something wrong here. So let me go here and let's do 0.0001 and drop it down super low. Okay, now let's go ahead and write quit. Let's try one more time, make. Let's go into particle output.dat. Okay, so these guys are not right. Not because he's 2015, great naming scheme. Okay, so let me also add 2 lines at the end here, which I totally forgot to do. So we're gonna do file, output. I can't believe I made that mistake. Gosh darn it. Okay. So let me go ahead and check up here. The member.positions seem to be... Did I initialize them at some position? Let me go up to where we initialized the group. Where are we? Group size, update phase. I may not have given them initial position. Let me see. Dance forward distribution generator. No, I did. They are all clearly in different positions here. Let me output something real quick. So we have group I. And let's do an std. std C out. Oop, that was a capital C. Group of I dot position. End line. Okay, let's write that. Let me go down to synchronize. Because he is synchronizing just fine. So no reason to output that. There should be a C out here. Let's go get rid of that. Go over here. Right, quit, make. Okay, so they are all clearly being generated between -10 and +10. So that's a little bit weird. Let me see, sim 0, not every update since big revamp, worse and worse. Okay, so what is the issue then? They have to have a previous position. Let's go into that update position guy. So where are we? Update position, where are we? Find accelerations. Let's output a whole bunch of different things. So let's see. We have member.acceleration, member.acceleration. Let's just do an std cout of all the member.accelerations. So std cout member.acceleration. Let's go ahead and end that. Now let's do a make. Okay, so all these accelerations are 0.001. All of them. They're all 0.001. That seems okay to me. Let me see. Customer didn't switch resolution too often. I missed that screen then. Sorry about that. Okay. So find acceleration is clearly getting the same acceleration for all of them. They're 0.001. Is that correct? Let me think. So, first of all, if this is a repulsive force, which it probably will be, then chances are some of them are going to be repelled one way and others are going to be repelled another way, right? So that's one thing that's a little bit weird about this. So we probably need to have some sort of x-hat direction in here. So what do we have here? Member acceleration. But that doesn't solve the underlying issue, that the positions are all forced into a certain, they're all 10. So let's go here and let me change this again. Let me put this a -10 here, because I had that wrong. And now let's do it one more time. Make. No, okay. Oh, well, no, that's expected. So now we're gonna do let's see, v particle output dot dat. Yeah, so we have some at 10, some at negative 10. In fact, many of these guys are at negative 10, but they're randomly generated, so that should be okay. Okay, so let me see. What is the issue then? Why are these guys not moving where they should? Well, that's a good question. Thanks for asking that. If we change the acceleration super duper low, I mean, it's already quite low, but if we change it even lower, I mean, we should be seeing these particles moving. Interesting. Okay. Let me see. What do we have then? Member dot position equals negative 10 equals 10. But why would they all be stuck at 10 and negative 10? They aren't all greater than 10. Maybe they do. Maybe immediately they have a higher position than what's allowed. So what do we have here? We have output positions group here of relay. We know the positions are being generated at the appropriate. I liked Rant on Visual Studio 2015. Okay, so what do we have here? Output position group Steve file. I guess what we can do, and we're already outputting the positions, right? And clearly after the relay algorithm, here's what I'm gonna do then. Let's not force it. Let's just kind of see what happens. Write this, go over here, write and quit, make. Okay, now let's go to vi particle output.dat. Okay, now these guys are good. They're good. So let's change the acceleration even smaller. I didn't expect it to be this small, but hey, what do I know about acceleration? Literally nothing. Okay, let's see, what do we have here? Let's go to add in an extra order of magnitude there, an extra order of magnitude here, because hey, I'm a physicist, that's what I do, orders of magnitude. Let's go ahead and DD here, DD there. Write this, go over here, write and quit. 1 second. Write and quit. And now I'm going to do make one more time. Okay, let's go into VI particle output.dat. Let's just keep adding in orders of magnitude. I feel like this should still do it okay. So let's add in another one here. Another one here. Write this, go over here, write and quit, make. Let's see, particle output.dat. Holy crap, are you kidding me? Let's try this, make. Nope, they are still locked in there. But let me check something. Okay, so we're gonna add this here. That there. Let's go here, write and quit. Make. Now let's go into particle output.dat. That's so weird. What are we outputting here? We are outputting... Wait, what are we outputting? This should be acceleration, shouldn't it? Let's go in particle output.dat. What is... I don't know what's happening. 1 second. Let me take a look here. Yeah, I have no idea. I actually like C# as a language, which can be compiled. It's okay language. If I missed something in chat, let me know. Just kind of put my name in the chat, and we should be okay. Yeah, TS Jost, I missed that a while ago. Thanks. Let me see. Yeah, so looking through the chat, I don't think I missed too much. But again, if I missed something important, let me know. I've been kind of missing some of it. Okay, so what is the issue here? I don't know. What are we outputting? Let's go ahead and check that out. So let's see. We have relay algorithm here. Let me do a look for all the C outs. We have C out there. We see out here member.acceleration. Aha. Aha. That is the member.acceleration. It's fine. Not a problem there. Member.acceleration is perfectly okay. However, the positions are still a little bit funny. Let me go to the relay algorithm. What do we have here? Member.position is equal to 2 times member.position minus member.previous position plus acceleration times dt times dt. Did I do something stupid here? Let's go into write and quit. One of the previous VIs that we've had. In fact, let me just do history. Grep VI. And let me do 513. Oops, my bad, exclamation mark. Now, let me see, what do we do for relay? Here we are there. And then we're there. 2 times particle position, minus particle previous position, plus particle acceleration times dt times dt. Yep. That's okay. Link is the best thing that happened to imperative languages. Let me see. Guys, let me get another quick sip of water. I'm super thirsty, but that's okay. It's also 6:30 in the morning. I guess we'll continue to figure out what's happening with the code, and then we'll go from there. Okay. So, the relay algorithm looks fine. I don't see what could possibly be wrong there. We're gonna quit. Okay, let's make it one more time. Of course, it's up to date. I actually managed to write some lock-free code that was faster with C# than C++, but only because GC beat me in reclamation performance. GC, what is GC? The new compiler? Is that what we're talking about here? Okay, what do we have then? So it seems to me that no matter what I do for the acceleration, let me just go ahead and run how to dance. So no matter what I do for the acceleration, it seems to me that these guys are moving quite far. So let me try this again. Let me go to member.acceleration. And it could be that we're not appropriately updating the member.acceleration somewhere. Oh, garbage collection. Sorry about that. I guess I could have figured. Okay, let me see. Member.position times 2. Okay, so when we do the relay algorithm then, let's output the member.acceleration there. So let's do stdc out. Member.acceleration. End line. And let's go down here and let's not output it here. Make. No, those seem like they should be okay. Old version of GCC. I'm sorry. I'm sorry. I didn't think about it at the time. Okay. I guess it's obvious looking at it. Okay. So the accelerations do seem to be times 10 to the negative 10th. Let me go up and not output the positions anymore. So let's go into cout. Should be one there, 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 there. Okay. So let's go ahead and write this. Okay, so what do we have then? All the accelerations also seem okay. They also seem okay. So then, what is the issue? Why are these positions changing so drastically? Well, I mean, they're all basically being forced to the same position every time. So let me go down here and let me see. Where's our? We found the accelerations. The accelerations are being updated. They're all basically 0. In fact, what happens if we just do? If we do member.acceleration equals 0 for this guy. So we do member equals 0. We do the same thing down here. We do member equals 0. Let's go over here and let's make that. Yep, so these are all 0. Now let's go into particle output.dat. That seems fine to me. Now let's go up here. Let's go and remove this line here, this line there. So all of these positions, okay, that's not right. That's not right at all. One second. What is the issue here? Oh, maybe that's the issue. Okay. Let me go up to, what do we want here? One second. Dance floor group oscillator dance floor. When we are creating this guy, we also need to do the following. So we'll say group of I dot previous position. It's going to equal to group of I dot position. Now let's try this. Right quit. Make. Now let's go into what happened here. There was an error. I just saw it somewhere up here. Oh, where'd it go? Here it is. Xdiff. Oh, that's fine. Okay, so now let's go into the particle positions. Okay, now they're all set to 10 again. Crap. But if we remove that, I don't understand what is happening here. We don't have an acceleration, so they all should be the acceleration that they were before, right? So it basically, they should have 0 acceleration, so they should be all in the same positions. They should not change position. Let's go right quit. Let's make that. Okay, let's go into particle position dot dat. And it looks like maybe they're not. Maybe the positions aren't changing. Okay, so outputting the positions. Yeah, those all look okay. 3.6, 3.6, 3.6, they're all 3.6. That should be okay. So why then, if we say member.position greater than 10, we set member.position equal to 10. That's the thing that's bugging me here. It doesn't make sense. All we did is we said, if we're greater than a certain limit, which we're not. Let me see. So let's go ahead and run this one more time. Make particle output.dat. Yeah, they're all forced to -10 and 10. What is the issue here? If member.position is greater than 10, we're definitely not greater than 10. Member.position equals 10. If member.position is less than, oh. Now let's make it. Now let's go to a.out. I didn't need to do that. Let's make it again. Whatever. Now let's go to particle output.dat. Okay, now we're set. Thanks, Eamon. I appreciate that. I'm an idiot, is what I am. Thanks for pointing that out, though. Okay, so now we have that. That's set. Now what else do we need to do? Linux version spoke to both of them, so that's something at least. Yeah, Linux version. Okay, so now what's next? Good, we have that set. Let's go ahead and change the acceleration again. I can almost guarantee this number is too small, so let's go ahead and just increase it a few orders of magnitude. So let's go here, right quit, and let's make that. Okay, so we have these accelerations. Now let's go to particle output.dat. 2.3, 2.3. These guys are barely changing at all. So let's go back up and let's change it again. Now let's go to make. Okay, so some of these guys, the accelerations are being set at -1 and 1. That means that we are clearly getting to the edge of the boundary. So let's go to particle output.dat. And let's see what happens here. 7.39 should be okay. Okay, so now what we need to do, or what I would like to do here, is go down to the very bottom here, and you'll see that a lot of them are stuck at the end of the boundary, but not all of them. And that's okay. That is okay. So now what I want to do is I want to output a couple of different guys. So I want to see how many time steps we go typically, and I just want to, I guess, just watch these guys move closer and closer. So let me go into the output position here. Yep. So what I want to do then, we need more channels like this on Creative. Thanks, man. Biggs by Norwegian. Thank you for coming in, and I apologize if I mispronounced your name. Okay, so what am I doing here? Particle output is that. Let me think. So we have all the particle data. I gotta think here real quick. What we need to do is we need to output all the particle data. Yeah, so we have all the particle data here. I'm just gonna open up new plot and see what happens real quick. So let me do new plot, and let's plot particle data with lines. Okay, that doesn't quite look like how I was hoping it to. What are we actually looking at here? It looks like 20. Oh, okay. So this is Steve. This is Steve. He is trying to, what is this down here? -10 to 10? I'm not quite sure what's happening actually. So this is a frequency. This is Steve's frequency. And his position shouldn't be changing. Oh, it's not changing. Okay. Okay. Yeah, I'm not really sure what's happening actually. I don't know. I don't know what just happened there. No idea. Okay, what I want to do is output a different graph. So what I want to output, I want to output the following. So let's go into particle output here. And let me think. So what I actually want is going to be hard to implement. What I want is a series of lines corresponding to each individual particle. So what I'm going to do is this. In particle output, I don't know whose idea it was for Twitch Android app to immediately disconnect from chat as soon as you minimize the video, but it's really annoying. I'm sorry, Gastorn. Okay, so what I want to do then is change how we're doing the output particles. So I'm going to comment this guy out for now. We'll read in that one file, that's okay, but we aren't going to actually be using that file for now. So let's go ahead and do, I guess, a vector of strings. So we'll do std the vector of string. And let me go up and make sure I'm reading in string. I am not. So let's go do include. I think it's just string, right? Yeah, sure, that should be okay. Pop down here. And what are we going to do? Yeah, that said, I mean, I don't know. It's kind of neat that they have the Android client, right? I mean, I don't know. I guess everything has an Android client now. I guess I'm not so surprised. Okay, so we need a vector of strings, and these are going to be file names. Names. And it's going to be of, let's do group.size. And yeah, I could generate this in another way. I get that. This is okay for now. So what are we going to do? We're going to say for, let's do int I equals 0. I less than group.size. And then we're going to do I++. Okay. What are we going to do? We're going to say the following. Okay. You might have to do std string. Let me just do std cout I then real quick. And let's make that real quick just to make sure that I didn't do something stupid. Yes, apparently I did. Vector string. String was not declared in the scope. Of course, std string. You were right. Okay, that one seemed to work okay. Good. Didn't rage quit Android development every time I tried it? No, I didn't, TS Jost. I did not. I'm using the standard string class there. Okay, 1 second. What do I want to do now? No, I'm not. I'm sorry. Okay, so what am I gonna do then? This is what I want to do. I want to say file string is going to equal to some base string. So this is going to be what do I want to do? I'm gonna call it file. Sure, that's okay. Plus i.cstring. Am I allowed to do this? I don't think this is how it works. Nope, no, because I is an integer. It wouldn't have a .cstring at all. 1 second. Let's add a semicolon in here. And I wanted to do stod. Is that right? Plus stod? Oh, it's probably stoi. I. Yeah, that was wrong. Let me see. I totally forget this stuff. But I'm trying. Oh, dagnabbit. No conversion from int to constant string. Fine. No magic function called stoi. Oops. Let me just do this. Let me do file names of I is equal to this. That fixed one of the errors. Now, no magic function call for stui int ampersand. Okay, let me go over here. Let me do something really stupid. How to convert int to string C++. Easy way to convert int to string in C++. As you can see, I've looked this up before. Character string int to a. Let me see. Is there an easier way? Let me see. std string s is equal to 2 string 42. That's what I wanted. Fantastic. std to... Is it str? Why not? Let's try it. 2 string. 2 string. I should have just went back. There we go. Make. Okay, works just fine. So now we have all of the file names. And what I want to do next is the following. So now we're going to say for. Oh, actually. Oh, this is initializing all the file names, isn't it? It's fine. It's fine. This will do. For int I equals 0. And actually, let's just go through all the members now. So auto ampersand member. What do I want here? Member. No, we need the eyes. We totally need the eyes. Do we? Yes, we do. Int I equals 0. I less than... Oh my gosh, I'm running out of time. Group.size. I'm missing some stuff. Java scared me off after uni forced me to use swing. I actually don't even know what swing is. I use no Java whatsoever. Guys, forgive me if I'm missing chat. I definitely apologize for that. I'm doing my best to keep up, but as sometimes I miss it. Hey, lol, it's been forever. How are you? Seriously, it has been a long time, like since 1975 almost. How have you been? Not 1975 almost, but it's been a few months, definitely. Thanks for coming back in, man. Okay, so we're going to group.size and we're going to do I++. Okay, so now what are we going to do? We're going to have to take another day for this, guys, just to make sure we have everything set, and then we're also going to have to do the visualization. Lots of things left to do, so if we don't finish today, we don't finish today, but I want to do at least one visualization. So what are we going to do then? We're going to say, what do I want to say? How about file names of I, output. Oh, that's incorrect. That is definitely incorrect. Okay, so what we need to do then is we need to say std vector, and there's more efficient ways to do this, guys, I know. Std of stream, and I guess we'll do output files are going to be equal to of size group dot size. Okay, let me think here. Just checking your GitHub. You have improved a lot in C++. Maybe, maybe not. It could be that Gustron wrote a lot of the code still. My favorite thing is that Android can pull initialize statics from under you if you minimize the app. Oh, okay. So what are we gonna do then? Output files group dot size. What do we have then? Should be okay. Everything should be okay. SD vector. Good. So now we have all the output files there. Now what we need to do is, I guess, initialize all the output files. How do we do that again? I always forget, literally every time. So let me go up here and let me check that out. I think it should be in main, I believe. SD upstream file. Particles.dat. Yes, so I guess what we'll do then is we will go down here and we will do the following. We'll say for int I equals 0. Then we're going to do I less than group.size again. I++. Pop down here. Now we will say the following. We'll say output files of I is going to be equal to... One second. I feel like I'm doing this wrong. But maybe it's okay. Let's just go here. And let's just do the following. We'll say output files of I. Wait, let me check that main again. There's main. SC upstream file. So I guess we would do this is going to be equal to file names of I. One second. I. And then we'll do std upstream out. Okay. And guys, basically I'm creating a whole bunch of files in the directory for every single person so that I can more easily visualize each person individually. That's what I'm trying to do. So forgive me if this is a little bit weird or not really making that much sense. Let me see. Comparison signed and unsigned integer error, no match for call. That's my question. I need to create a vector of std upstreams. Just checked. Yes. So good. I've especially decided not to do any Android support until pure 64-bit as possible. Yeah, I don't know much about that. No match for call. Okay, so here's what we need to do then. Zephyr. AIDS? I don't know what you mean by that. I apologize, maybe you're not a native English speaker. A lot of people aren't native English speakers, though, so please don't worry about that. Feel free to say whatever you want in chat. Okay, so we say output files here. So maybe what I should do is going to be equal to... One second. I gotta think here. Std upstream output files of size group size. So we'll say this is going to be equal to... Wait, what do I need to say this is equal to? Gosh darn it. Again, I just want a series of files. I feel like I've done this before. When have I done this before? Let me go into VI, color quantization, and let me see, what do we have here? Nope, that's all not what I want, but maybe color quantization.c. So let's go into VI, color quantization.cpp. And let me see, vector of upstream, do I have, or outstream? So, in file, temp, eyeball. Let me see. Loyola 19, I imagine it's true for pretty much all programs. Oh, okay, so what are we doing next? Pragma on parallel for num threads. Maybe I didn't. Dag nabbit, when did I do this? Still worth spending time and effort. Okay, wait. I need a vector of output files. That's what I need here. So if we have SC vector of output files, that should be okay. So this is gonna be calling each of those guys. So what we need to do then, let me go up real quick to the top here. What we need to do is we need to initialize each of these guys. Okay, so what I might do is something really stupid here. Upstream file. And I might say the following. I might just do this. I might say vector.pushback. Where we were in output positions. So I might do output files here. And then I'll do output files.reserve. Let's go down. Ooh, that wasn't what I wanted. Output files. .reserve. 1 second. And I guess we're going to do group.size. Okay. And what I want to try... Yeah. You should do in-place back. So let me try. Output files. Yes. So I guess I need to try... output files i.open file names. Okay, let me see. So let's do output files. .inplace back, maybe? Again, I might be doing this wrong. I'm trying to think. Make, okay, that one seemed to make at least. So that's good. So now we have all that. Now we're gonna have to close them all in the end. So let's go ahead and loop for closing all. Yes, good. Everything. Okay, so now we're gonna do for, I guess we'll do auto here. Ampersand file in output files. Oh my gosh. I have like 10 minutes. I gotta get this done. Output files. Now we're gonna do the following. We're gonna say file.close. This should be okay. Now let's go up here and let's output all the stuff. So we're gonna say, we have all the group members. What do we need to output? We need to say the following. We will say output files of I Oh, that's probably true. It's okay, it's okay. It's going to be equal to group of I IC.position, new tab. Actually, no, I just want group of I.position, and that should be okay. So we want new line, and that should be good. So let's go here, make. I misspelled close. Make. Let's do an ls. Seemed to work. Okay, so now let me just open up VI file 0. Oh. It's a -10. Let's also output this guy. It's only 1 -10. Oh, but maybe that's okay. Make it again. Oh, you know what's happening? Probably every time we're opening this guy up. Yeah, so we need to append the data. How do we append the data instead of reopening up the file and destroying everything? I mean, Make. Okay, so now we have to find a way to append the data to these guys. Let me see. Is there a way, let me see, appending data to file. C++, see what we got here. I have to append text. I think it's probably just not out. Let me see, what do we have here? std, where are we? Is appending not, is that hard? 1 second. IO mode append, let me see. Fstream, name ios.app. Is there, can I just do Fstream append? Is that a thing? App. Okay, let's try that. Let's go to make. Now let's go into vi file 0. Okay, good. So this guy's position seems to be changing, and this should be good. So let's go ahead and remove. I'll load you an ls real quick. And we're going to remove everything that has a file in it. So remove file. That should be okay. File star. Now let's go up here and let's change the file names to be something .dat. So we're going to do plus .dat. Just so I have a common data file. And now let's make that. Okay. Finally, let me do an ls and let's run into new plot. Okay. Now let's go ahead and plot. 1 second. File 0. .dat, and good. Okay, this is what I wanted to see. With lines. Okay, so here's what's happening. And let's just plot a couple of these guys. So we have 20 people. So let's go ahead and do file 19. Okay, good. So, and we're just going to continually replot. So we're going to do replot. File, let's do 0. Just a couple guys. 0. Let's do, I don't know, 10. And let's do 12 or something like that. Oh, not 112. Let's just do 12. And let's do, I don't know, like 15. Okay, so this is a whole bunch of people. Just representing a number of people in the simulation. Here's what's happening. Well, okay, kind of. So here's what's happening. We have this guy. His name is Steve. He's in the middle of... Yeah, each one's being graphed. That's exactly what's happening. So here, let me just explain the simulation that we've done so far, because actually we're near the end of the episode, so this is probably a good point to just go ahead and close things. So here is the simulation that we've done so far. I realized that people popped in the middle. I apologize for that. My stream doesn't work very well when people pop in the middle, but that's okay. So here was the idea. We have this this guy. His name's Steve. Steve is socially awkward and doesn't know how to dance. So what ends up happening is Steve wants to be socially accepted, so he goes to a party. When he goes to the party, he sees a whole bunch of people, all of them oscillating. Here's this guy dancing, 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 this guy dancing. And because they all know how to dance, they are all oscillating at the same frequency, right? So they're all oscillating together. Steve then decides that he's going to pop right in the middle of the dance floor, and he's going to start dancing. Unfortunately, he doesn't know how to dance. He has no idea how to dance at all. So he's dancing really awkwardly, and everyone is repelled away from him because he is such a bad dancer. He is actually downright awful at dancing. So everyone's repelled away from him, and that's exactly what you're seeing in the simulation. What you just saw were a whole bunch of people who were being repelled away from Steve. And moving to the edge of the dance floor. So here, we have one guy who starts at this position, and he's being forced over here, and this guy is being forced over here. And basically what we're seeing is all of these guys being repelled away from Steve. Reason we did this is because I wanted to show how a Kuromoto Oscillator works. So if you're not familiar with the Kuromoto Oscillator, which you might be if you know physics, but you might not be if you don't, let's do new page before. The Kuromoto Oscillator works like so. So we do Kuromoto Oscillator. 1 second, 2 L's. And here's the idea. We have some sort of change in its in phase. And this change in phase is a change in phase dependent on time. That's what a dot means. And it says it's going to be equal to whatever frequency our individual character has, so some sort of resting frequency, plus a sum of all the other characters in the simulation. So we'll say j equals 1 to n. And some sort of function that is dependent on the change in phase. Oh, sorry, there's no dot here. I and j. Okay? And typically this is like a sine or something like that. We used a sine in our simulation. So it's sine, and actually we did j first, minus theta I. And here we actually see two things. One, we see Steve slowly but surely getting better at dancing, and then we implemented... Yeah, okay, I'm sorry. My handwriting's not that great. That didn't help any. Anyway, point is, yeah, so we see two things in this simulation. One, we see Steve's frequency slowly getting better and better, and two, we see everyone being repelled away from Steve. Now, tomorrow, we're implementing the next bit of this algorithm, the redemption of Steve. So in the first case, everyone is being repelled away from him because he's horrible at dancing. In the second case, what's going to happen tomorrow is we're going to see people slowly start to come back to Steve as he gets better and better dancing, and they'll start to crowd around him, and it's going to be a happy, good thing. Everyone's going to be happy. It's going to be super happy. Anyway, I kind of wanted to see how hard it would be to, how do I put this? I want to see how hard it would be to basically filter things based on frequency. And this is kind of what we're doing in a way, right? Because in a sense, what we're doing is we're forcing everyone into a certain position based on how they're moving. And that's very important for a number of different things that we'll run into later. In particular, we'll run into something quite similar to this with genetic algorithms, which we're going to be covering quite soon. So I thought it was kind of interesting as a way to kind of do things, you know? And we'll see what happens. Anyway, guys, it is 7 o'clock in the morning. We are currently seeing what I want to see with the simulation. Everyone's being repelled over to the edge of the dance floor. So tomorrow we will get back to it. We will watch everyone be attracted back towards Steve, and we will be able to see basically a time plot of everyone go out and then come back in. And then we'll go from there. Yeah, Gustron, I do intend to hit genetic algorithms relatively soon. They're super important for a number of different things. I just have trouble understanding them, so I kind of wanted to hit something... That's kind of what we're going to be doing in just a second. Anyway, thanks guys so much for watching. As always, have a great day, night, afternoon, morning, evening, whatever time it happens to be your time. Genetic algorithms. Rank quit. And before I leave, I'm going to go ahead and do git commit howtodance.cpp. And I'm going to add this to github.m. Adding the ability for dancers to be repelled from Steve. Whatever, that's good. Then we're gonna do git push. Origin master. And of course, you guys now have access to this on github.com. Feel free to go ahead and take a look. Anyway, guys, thank you so much for watching, and I will see you guys around next time for the next episode, where we start again at 5 o'clock in the morning my time, end at 7 o'clock, and we basically finish up this simulation. We're going to take a day or two to do the visualization, which I think will turn out kind of neat. You know, this is my first try at like telling a story to teach an algorithm, so we'll see if that helps or if it doesn't help, you know? If it doesn't work, it doesn't work. If it works, it